Hey, Bill here. So have you ever considered what would happen if we connected the output gate of a NOT circuit to its input gate? Remember, the output of a NOT gate outputs 1 if the input is not 1 and vice versa. But if you tie the two ends together, what happens? This is one of those questions you can't answer without stepping down a level of abstraction. This is a case, in other words, where encapsulation lies to us, and we're better off looking at the underlying components. So what happens is this. When the input voltage goes up, the output voltage goes down, and vice versa. At some point, the two voltage lines cross. Now, if we connect the input and the output together, the transistor will settle at this crossing voltage. It then sits there at this voltage, not really on, not really off. That crossing voltage is stable, meaning the voltage won't budge. Temporarily putting more voltage on the line won't cause the transistor state to change in the long run. Now consider what happens if we add two NOT gates in a row. Again, let's drop down a level of abstraction. We'll add a variable resistor to each of the inputs so we can control the input voltage. Currently, the resistors are effectively infinite in the displayed circuit. The interesting part is that our circuit is stable. The left side is on because the left transistor is off, and the left transistor is kept off because the right transistor is on, driving the right side's voltage to 0. Now, if we adjust the variable resistor on the left, we can drop the voltage on the left, which feeds the transistor on the right. Remember that our transistor is an amplifier, so a small budge on the left won't really influence the state of our circuit. If we pull the voltage on the left down enough, by lowering the resistance on the left, the transistor on the right starts to increase in resistance, and enough of a drop causes the transistor on the left to change. However, if we drop the voltage enough, suddenly our voltage changes state. The lowering voltage on the left turns off the transistor on the right. That causes the transistor on the left to turn on, and the transistor on the left takes over for the variable resistor on the left, keeping the transistor on the right turned off. This keeps the transistor on the left on, and our circuit has changed state. Voltage on the left is 0, voltage on the right is full on. And this is stable. Because the transistor on the left is now on, it doesn't matter what we do with the variable resistor on the left. The transistor on the left keeps the voltage on the left at 0 regardless of our variable resistor. In fact, we can only change the state back if we drop the voltage on the right. This causes the state of our circuit to flip back. For the transistor that is on, as long as the voltage supplying that transistor remains above our threshold voltage, the circuit wants to pull the voltage up to the full on voltage. If, however, its voltage falls to the lower region below, the circuit will change state. So, in our example, if we use the variable resistor on the left to pull our voltage down, as long as it stays in the upper region, the state of our circuit won't change. But if we pull the voltage down enough, our circuit changes state. This phenomenon is called bistability because it has two stable states, one where the left is on and the right is off, another where the left is off and the right is on. Suppose we want to use this property of bistability in our circuits. Remember that a transistor is like a variable resistor that changes its resistance as voltage is applied to its base. So we can replace our variable resistor with a transistor. When we do this, notice something interesting about these two circuits outlined in yellow. They're the same as our NOT or NOR gates from a prior video. So let's redraw this using two NOR gates. We call this a set-reset flip-flop, or set-reset latch. As a side note, the terms flip-flop and latch tend to be used interchangeably in computer science circles. Our set-reset flip-flop circuit has two inputs, a set input and a reset input, and it has two outputs, customarily labeled Q and not Q. When the set line is turned on, our circuit changes state, and Q is turned on while not Q is turned off. This state is stable. Turning the set line on and off again doesn't change anything. We can reset the state of our circuit by using the reset line. This turns our circuit off. And we can change the circuit back by using the set line again. Our circuit, by the way, is completely symmetrical. Our calling one side set and the other reset is purely convention. As we have done before, let's tally up this behavior by drawing a table. When the set line is on, then the Q line is set and the not Q line is cleared. When the reset line is on, then the Q line is cleared and the not Q line is set. If we clear both, of course, then there are no changes in the state. Either Q or not Q remains turned on. Now, if we set both set and reset, we turn off both transistors simultaneously. This turns off both Q and not Q, but then which one turns on when we turn set and reset off depend on a number of factors, including the timing of when we release the lines and the imperfections in the transistors and resistors. We consider this state illegal, not because it's somehow against the law, but because we don't know what will happen next, and this lack of predictability is not really all that useful. One way we can avoid this indeterminate or illegal state is to use some logic circuits to prevent this from happening in the first place. For example, this collection of circuits guarantee that only one of the set or reset lines are turned on. We call this a D flip-flop or data flip-flop because when the enable line is turned on, the data line either sets or resets our flip-flop. Let's tally these results up in a table. If the enable line is turned off, it doesn't really matter what the data line does. The output doesn't change state. Customarily, we represent don't matter by using an X. If the enable line is set while the data line is clear, then the output Q is clear and not Q is set, even after the enable line is turned off. If the data line is set while the enable line is set, then output Q is set and not Q is cleared. And as always, we can encapsulate our circuit in this box. Now, if we put two of these in a row with a NOT gate wired between the enable lines, we create a new gate that has some very interesting properties. As long as the enable line is clear, the first gate does not change its state. When we turn on the enable line, changes in the data line affect the first gate. But the enable line to the second gate is turned off, so changes to the data line don't affect the overall output. But now watch what happens when we turn the enable line off. The contents of the first gate is now allowed to be latched into the second gate. And so long as we leave the enable line off, if the data line changes, the output of our system doesn't change. We call this an edge-triggered D flip-flop because the contents change not when the enable line is on or off, but when our enable line changes from on to off. Customarily, we label the line that changes the state of our circuit with a C for clock to signify the fact that our circuit changes state only when the data is, quote, clocked in by changing the state of our clock line from on to off. So long as the clock line is on, the output state doesn't change, but when the clock line turns off while the data line is off, the Q line is cleared and the not Q line is set. We use this down arrow in our table to indicate the behavior happens only when the clock line drops from 1 to 0. Now, resetting our clock, we can set our Q and clear the not Q lines when the clock line drops from 1 to 0 while the data line is set. Now, the circuit we just showed changes state when the clock line goes from 1 to 0. We can change this to store the contents when the clock line goes from 0 to 1 by adding an additional NOT gate. And of course, we can encapsulate this in another box. We now have an edge-triggered flip-flop which can store the contents of our data line on the edge of our clock at the precise moment when our clock input changes. Now hang on, what do we mean by precise moment? To the naked eye, when the input signal changes in one of our circuits, the output signal appears to change state immediately. But when we consider what happens to our circuit on the scale of nanoseconds, we see an entirely different story. At the scale of nanoseconds, electricity acts more like water filling a pipe. Even though the signal was turned on, it takes time for the signal to change due to capacitance in the wire. Capacitance is, in essence, the capacity of a component to store electricity, and while the capacitance of our input wire is extremely small, at the scale of tens of nanoseconds, it matters. Once enough current has filled the wire and started filling the gate of our transistor, the transistor itself changes state, allowing current to flow out of the emitter of our transistor. While the transistor itself may switch faster than the input current, the capacitance on the output wires slow the change in the signal. The amount of time it takes for our transistor to switch state, then, is not instantaneous. It takes time, albeit tens to hundreds of nanoseconds, depending upon the type of transistor, for our transistor to change state. We can, of course, speed this up. By making our transistor smaller or by making wires thinner, we can make our circuits much faster. And in today's modern computers, transistors are often only nanometers in size. But even then we run into other limitations. At the scale of today's modern computers, a 3 GHz microprocessor executes a clock cycle in 1/3 of a nanosecond. And in 1/3 of a nanosecond, light can only travel about 4 inches, and nothing travels faster than light. So this means no matter what we do, we still have to contend with this delay, and this delay happens in every single transistor for every single circuit we build. So this means for an edge-triggered flip-flop that is latched around our clock signal, our data input line must hold a constant value for a small window of time before and after the transition in order for our circuit to work. For our D flip-flop, this generally means there is a window of time before our clock signal changes, the setup time, for which our signal must be set prior to changing the clock signal. And after our clock signal changes, our data signal must continue holding a constant value for our circuit to work. This time is generally measured in microseconds or nanoseconds, but it does limit how fast our computer can operate. Any faster, and our transistors don't have time to switch correctly. And often these times are found experimentally. That is, we actually build the circuit in a lab, then increase the speed until our circuit fails. Now, if we take our data flip-flop, we can wire 8 of these in a row and build a device which can store 8-bit binary values. These registers can be used to store intermediate values in our computer. There are other circuits we can create around our set-reset flip-flop, circuits which will become handy as we build our computer. For example, we can take a couple of AND gates and add an enable line which needs to be turned on in order to set our flip-flop. So long as our enable line is turned off, any change to our set-reset flip-flop will not result in any changes. Further, if we enable our flip-flop but leave the set and reset lines turned off, then we also don't experience a change. If the enable line is set, then the set and reset lines will change the value of our gate as before. And of course, if we set all 3 lines, we are in an illegal state. We can't predict what will happen next. We can, as always, encapsulate this in a new box. We can put 2 of these gates in a row to create an edge-triggered set-reset flip-flop, and we can iterate through all of the states in a table. Like our edge-triggered data flip-flop, our edge-triggered set-reset flip-flop does not change state unless the clock line changes from on to off. These edge-triggered set-reset flip-flops are quite useful, and we can encapsulate this new flip-flop in its own box. One thing we can do with our new flip-flop is to add a little logic that wraps back to our output. This gate was named a JK flip-flop by its inventors, and it has the very interesting property that it acts very much like our edge-triggered set-reset flip-flop. When the clock changes and either the J signal or the K signal are on, we set or clear the Q and not Q lines. But notice what happens when we set both J and K. The AND gates select the set or reset line depending upon the prior state of our flip-flop. This has the net effect of toggling which output is set. And as always, we can encapsulate this in its own box. As a side note, this circuit is named a JK flip-flop because its inventor had invented a number of flip-flop circuits, naming the first an AB flip-flop, the second CD, and so forth. Now, if we take our edge-triggered set-reset flip-flop from before and simply hook up the outputs to the inputs as shown, we get a T flip-flop or toggle flip-flop. What a T flip-flop does is very simple. When the clock signal transitions from high to low, the state of the output flips state. We can show this in a table, though the table is very simple. It toggles when the state of the clock line drops from high to low. And as always, we can encapsulate this in its own box. An interesting thing about these T flip-flops, if we wire up 4 in a row as shown, the first flip-flop toggles when the input clock goes from 1 to 0. The next flip-flop toggles when the last flip-flop switches from 1 to 0, and so forth. This gives us a simple counter. It counts the number of times the input clock signal transitions from 1 to 0. There are other useful gates we could build with our components using the same principles we've shown here. For example, we could build a counter that counts down by changing our T gate to transition when the signal goes from 0 to 1. We can add some additional logic to create a counter that can also store a number. We can use the T gate to create a frequency divider, a circuit which toggles at half the speed or a quarter of the speed of our input clock, and so forth. But all of that will be for a different day. In this video, we covered set-reset flip-flops and how they work. We covered how to convert a set-reset flip-flop into a data flip-flop and how we can use that as a register to store binary values. We covered a variety of other flip-flops, including edge-triggered set-reset flip-flops, JK flip-flops, and T flip-flops, and how to use that to build a counter. We also covered the reasons why computers have speed limits by discussing how transistors do not switch state immediately, but are limited by things like capacitance and even by the speed of light itself. In our next video, we'll discuss a little bit about how to put our 8-bit registers and our arithmetic logic unit together to start building our computer. Thanks for watching.